Number two is a problem that's just basically built on the first one, and it's asking for the integral of 1 over a function that, well, it's not exactly the same as 1 over x, so we can't treat it as the same. What we need to do is we need to do a u substitution on the denominator to make it 1 over u. So this becomes u is equal to 5x minus 2, du is equal to 5 dx, which means that dx is equal to du divided by 5. And that gives me 1/5 integral of 1 over u du. And now we can transfer this to become 1/5 times the natural log of the absolute value of u plus c, or 1/5 natural log of the absolute value of 5x minus 2 plus c. And that's it. Number three asks for the area bounded by the graph of y is equal to x over x squared minus 5, the x-axis, and the line x is equal to 1. So given that, I'm going to need to have more than a few things happen here. I need to, well, let's see. I'm trying to see if it can actually give me a, nope. I didn't know if this program could give me a grid. We'll just draw one. Oh, I guess I can just do it this way. Okay, we'll make this 90 degrees and we'll do a grid. I'm putting this in there because I want my grid to be pretty solid, but I don't want anything else to kind of mess it up. So this is going to be an XY axis just to kind of get an idea of what this is going to look like. And I want to graph what I know about this. Well, what you may remember from pre-calc is that you have an x-intercept of 0, 0, and you have vertical asymptotes at x is equal to 2 and x is equal to -2. I also know that if I do a sign test on the factored form of this, x minus 2, x plus 2, if I do a sign test, I have 0, 2, and -2, and I know the graph is positive to the right of 2, negative, positive, negative. And I know that as x approaches infinity, as x gets really, really large, y approaches 0, because the limit as x approaches infinity of x over x squared minus 4 is equal to 0. That's from limits from last year, that the degree of the denominator is greater than the degree of numerator, which is basically saying that as x gets really big, this approaches 0, and it actually occurs on both sides. If I plug in negative infinity, the same thing would hit. So all of this puts together to a graph that looks like it's positive as it approaches 2, and it's completely captured by this. It's negative on the other side of 2, crosses through the x-axis, and then continues up to the positive side as it approaches -2. Then it's negative entirely left of -2. So this gives me an image of what the graph looks like, and it operates as an excellent review of stuff that you did before. I also know that if x is equal to 1, y of 1 is equal to 1 over -3, or -1/3. So zooming in on all of this, we have a graph that really is depicted by, so 1, -3 is a point. So really this graph kind of needs to sort of go like that. But the part that's bounded by the x-axis, the line x equals 1, and the graph is just a little triangle there. And that's the part that we're going to focus on with this integral. I'm going to do the integral, maybe I'll stay zoomed in here, the integral from 0 to 1 of x over x squared minus 4 dx. And if I do that integral and do u is equal to x squared minus 4, du is equal to 2x dx, it's going to cancel the numerator, and I'm going to pull out the 1/2, and I get a 1/2 times 1 over u, which the integral of that's going to be the natural log. So the natural log of the absolute value of, oh, hang on, let me back up. Let's just do, I forgot to change my limits, and just do this completely as a limit change. 1/2 integral, plug in 0, I get -4, plug in 1, I get -3, 1 over u du, which gives me 1/2. The integral of 1 over u is the natural log of the absolute value, so then ln of 3 minus the ln of the absolute value of 4, which is just the ln of 3 minus the ln of 4, obviously in parentheses. And then this would be negative, and that makes sense because this was below the x-axis. So the area, we'd have to switch that around and make it 1/2 times the ln of 4 minus the ln of 3. And then the only way to clean that up is actually just to say ln of 4 is the same as 2 times the ln of 2. So then maybe I could say the ln of 2 minus 1/2 the ln of 3. Okay, next bit, number 4, was the integral of 3x squared plus 1 over x cubed plus x. And this can just be a straight up u substitution on the denominator, x cubed plus x. Du would then be 3x squared plus 1 dx, which would perfectly cancel out the numerator and give me the natural log of the absolute value of x cubed plus x plus c. And you can skip right to that on problems like this. Number 5 was the integral of the secant squared of x over the tangent of x dx. And the u, the derivative of tangent is secant squared. So if I let du be equal to the secant squared of x dx, that's going to also cancel the numerator out and give me 1 over u, and the integral of that is the natural log. So this is the natural log of the tangent of x plus c. And finally, for number 6, you have x plus 2 over x squared plus 4x dx. And the first thing we're going to try with this is just a u substitution of the denominator. And if I do that, I end up with 2x plus 4 dx, which is the same thing as factoring a 2 out and getting that x plus 2 I need to cancel the numerator. Pull the 1/2 out. The integral would then be the natural log of the absolute value of x squared plus 4x plus c. And I would have to keep these absolute value bars because if x were -1, for instance, then I would have a negative inside. So I can't just make these be curved because there is a chance that the inside could be negative. We can't take the natural log of the negative number. So hope that helps.